Greetings everyone, my name is Avanish Rao and my matrix number is B0920103994 and I'll be explaining on the introduction. So first is the theory. As you guys know, in this lab we'll be using the structure of a disc brake. So the disc brake actually has a metal disc or rotor instead of a drum. It uses a pair of flat line shoes or pads that are forced against the rotating disc to produce braking. The pads are held in a caliper that straddles the disc. The caliper has one or more pistons with a steel and dust boot for each calipers. So next is the working principle. During braking, the hydraulic pressure behind each piston pushes it outward. This forces the pad into contact with the disc that results in a frictional contact that slows and stops the disc and wheel of the vehicle. If pads on one side are worn more severely than the opposite side of the vehicle, the piston may be stuck into the cylinder of the opposite caliper. Brake disc should always be renewed or refinished in pairs. Doesn't matter both front or both rear disc, even if only one is damaged or defective. So next we will move on into the safety factor. A factor of safety is related to the safety of people. It reduces the risk of failure of a component by adding some cushion in the design. So the safety factor or factor of safety provides protection against those unknown events to some extent. Although all components are designed with a factor of safety, it's always suggested to use those components within their design limit. So basically, the formula of safety factor that is being used in this lab is ultimate stress over the allowable stress. And as you can see, this is the figure of the safety factor that is being used in the CAD software during our lab. So next I'll be giving a brief explanation on the procedure and also the work process. So first we have to of course design the disc brake rotor based on the given drawing using the CATIA V5 software, and this is the picture that is given in the lab sheet. So we will be designing the rotor disc based on the dimensions given. For example, there is this diameter and radius and also the length of each side of the rotor brake. So as you can see, there is A 360, B 34, C 31 if I'm not mistaken, D 59.7 and so on. So we'll be designing the rotor disc based on this picture and given dimensions, and then we'll be moving on into the structural analysis. In the structural analysis, we will be depending on the constraint at the part that is attached with the nut at rotor disc, and then we will be applying a load about 2680 kN on the brake pad area, and then we will be running the structural analysis in the CATIA V5 software, and we will be listing down the result for each stress and deformation in the table given in the lab sheet, and that will be explained by my friends groupmates later. And this is the picture of the rotor disc during the structural analysis in the CATIA V5 software. That's all from me. Thank you.
Okay, hello guys. Let's see how to analyze this brake rotor. First of all, select the start button and choose the analysis simulation. Click the generative structure analysis. Click OK. Make sure it is good version. Okay. And the middle part of the brake rotor. Move it. You need to get the exact middle part. So press OK, and surface slider in front of the rotor, and then back of the rotor. Click OK, and then we need to distribute the force. Was 1680. Make sure the arrow in inside position. So my arrow was inside position. Click OK. The direction was correct. And the force need to apply at both sides. So this is also. Make sure the arrow in inside direction. If the arrow was correct direction, click OK. Then complete the analysis. Click OK. Wait a moment. Okay. Yes. And click insert frequency case. Click the static case solution. Unclick the meshes. As the reference, you need to click the static case solution as the reference. Click OK. Compute all the thing. You want to continue the competition. Yes, okay. Wait a moment. And this, you can see the analysis now. So this is our one misses stress. This is our transitional displacement vector. This is our stress principal tensor symbol. That's all. Thank you very much. Hello everyone, my name is Shasivaran Anarki Sundarajan. My metric number is B0920104050. Today I want to define about our rotor disk material properties. First of all, let's see our Young models material. Our Young models material value was 2.11 exponent of 11 Newton meter square. And the Gaussian ratio is 0.291 and the density is 7870 kg meter square, and the thermal expression is 1.21 exponential of 5 Kelvin degree Celsius, and the yield strength is 3.1 exponent of 0.008 Newton per meter square. The material we use is cast iron. So now let's see our structure analysis. This is our structure analysis. Minimum displacement and one misses stress. So let's see how it's great. For the maximum one stress is 1.44 exponent of 0.0006 Newton meter square. The minimum one stress is 975 Newton meter square. The transitional displacement is 351 mm. Thank you very much.
Hi, Assalamualaikum. My name is Muhammad Zafaran bin Zeroyi. My metric number is B0920102060. So I will tell you about our lab discussion on the break this rotor. So as you can see, von Mises stress is a value used to determine if a given material will yield or fracture. It is mostly used for ductile materials such as metals. So same as our lead rotor disc brake, it is made from metals. So the von Mises yield criterion states that if the von Mises stress of a material under load is equal or greater than the yield limit of the same material under simple tension, then the material will yield. So for the factor of safety, it is usually refers to two things, which is, for the first one is the actual load bearing capacity of a structure or component, and the second one is the required margin of safety for a structure or component according to code law or design requirement. So for the equation on a factor safety, as our lab disc brake rotor made from metal, so it is equalized for ductile material. So the equation is factor of safety equals to yield stress and divide by working or design stress. So that's all from me. Thank you.
For the factor of safety, we use the formula ultimate stress divided by max allowable stress. The ultimate stress we get from the analysis from our drawing, and for max allowable stress we get from properties of material. So the safety factor we get is 4.65 exponent negative 3. Is below than 1, so it's slightly failure.
Next, for the conclusion, in this lab we were able to design the disc brake in virtual reality by using CATIA V5 software. In addition, we learned how to define material characteristics based on brake force that are suitable for disc brake rotors. As a result of our design research, we discovered that the factor safety value for the disc rotor that we have obtained is less than 1. The disc rotor has a minimum factor of safety of 1.5. By modifying the thickness of radius and material type, we can enhance the value. That's all from us. Thank you very much.